potential for life on Mars is a key focus in astrobiology, given the planet's proximity to Earth and its similarities. While no definitive evidence of past or present life has been discovered, research suggests that during the ancient Noachian period, Mars had liquid water on its surface and may have been habitable for microorganisms. However, habitable conditions do not necessarily indicate the presence of life. Scientific efforts to detect life on Mars began in the 19th century and continue today through telescopic observations and robotic missions. These investigations focus on identifying water, chemical biosignatures in Martian soil and rock, and biomarker gases in the atmosphere. Mars is particularly valuable in studying the origins of life due to its resemblance to early Earth. Unlike Earth, Mars has a cold climate and lax plate tectonics, meaning its surface has remained relatively unchanged since the Hesperian period. With at least two-thirds of its terrain older than 3.5 billion years, Mars may have been habitable as early as 4.48 billion years ago, 500 million years before the earliest known life on Earth. This makes Mars a crucial site for understanding prebiotic conditions, even if life never existed there. Following confirmation of Mars' history of liquid water, rovers such as Curiosity, Perseverance, and Opportunity have been actively searching for signs of past life. Their investigations focus on ancient biospheres that could have supported autotrophic, chemotrophic, or chemolithoautotrophic microorganisms, as well as former river and lake environments that may have been habitable. Today, the search for habitability, fossils, and organic compounds on Mars is a top priority for space agencies. Recent discoveries on Mars have fueled interest in its potential for past life. Organic compounds found in sedimentary rocks, along with boron, a key element in prebiotic chemistry, strengthen the case for early habitability, particularly in Gale Crater. Evidence of ancient liquid water further supports this possibility. However, Mars' present surface conditions are harsh, with high levels of ionizing radiation and toxic perchlorates in the soil. As a result, if life ever existed on Mars, scientists believe it would be best preserved in the subsurface, away from these extreme conditions. In June 2018, NASA detected seasonal variations in methane levels on Mars, a potential indicator of biological or geological activity. The European ExoMars Trace Gas Orbiter began mapping Martian methane in April 2018, while the Rosalind Franklin ExoMars rover was scheduled to analyze subsurface samples before the program's indefinite suspension. Meanwhile, NASA's Perseverance rover, which landed successfully, is collecting drill samples that may eventually be returned to Earth for analysis in the late 2020s or 2030s. As of February 8, 2021, new findings on potential life detection via phosphine on Venus and methane on Mars were reported. In October 2024, NASA announced that photosynthesis might be possible within dusty water ice found in Mars' mid-latitude regions, further expanding the possibilities for sustaining life. Mars's polar ice caps were first discovered in the mid-17th century. By the late 18th century, astronomer William Herschel demonstrated that these ice caps expanded and contracted with the seasons, growing in winter and shrinking in summer for each hemisphere. By the mid-19th century, astronomers had identified additional similarities between Mars and Earth, such as the nearly identical length of a Martian day and the planet's axial tilt. This tilt meant Mars experienced seasons like Earth, though they lasted nearly twice as long due to its extended orbit. These observations fueled speculation that the planet's darker surface features might be bodies of water, while the brighter areas were land, leading to widespread curiosity about the possibility of life on Mars. In 1854, William Whewell, a fellow of Trinity College, Cambridge, theorized that Mars had oceans, continents, and potentially life. Speculation about Martian life surged in the late 19th century when some astronomers reported seeing what appeared to be canals on Mars, features that were later revealed to be optical illusions. Despite this, American astronomer Percival Lowell published Mars in 1895 in Mars and its canals in 1906, proposing that these canals were evidence of an ancient Martian civilization. His theories inspired British writer H.G. Wells to write The War of the Worlds, 1897, depicting an invasion by Martians fleeing their drying planet. However, skepticism grew. In 1907, British naturalist Alfred Russel Wallace published Is Mars Habitable? As a direct rebuttal to Lowell's theories. Wallace concluded that Mars was not only devoid of intelligent life, but was entirely uninhabitable. Historian Charles H. Smith later recognized Wallace's book as one of the first contributions to the field of astrobiology. Scientific observations further challenged the notion of a habitable Mars. In 1894, American astronomer William Wallace Campbell conducted spectroscopic analysis of the Martian atmosphere, finding no evidence of water or oxygen. The final blow to the canal theory came in 1909 when Eugene Antonidi, using the powerful 83 centimeters telescope at Newton Observatory, found no trace of canals. Around the same time, high-resolution photographs taken at the Pic-du-Midi Observatory further discredited the idea. By the early 20th century, the Martian canal theory had largely fallen out of favor, shifting scientific focus toward more evidence-based approaches to studying the planet. Mars' environmental conditions are shaped by a combination of chemical, physical, geological, and geographic factors. While isolated measurements of these elements may not be enough to determine whether an environment is habitable, their collective assessment can help identify regions with greater or lesser potential for habitability. Currently, two ecological approaches are used to predict the habitability of the Martian surface, each considering 19 or 20 environmental factors. These models prioritize water availability, temperature, nutrient presence, energy sources, and protection from solar ultraviolet and galactic cosmic radiation. Scientists have yet to determine the minimum number of parameters required to assess habitability, though they are certain it exceeds just one or two factors. Likewise, the specific thresholds for each parameter remain under investigation. Laboratory simulations indicate that when multiple lethal conditions are combined, survival rates decline dramatically. However, no comprehensive studies have yet been published that simulate all biocidal factors on Mars together. Additionally, the possibility that Martian life, if it exists, relies on a fundamentally different biochemistry than life on Earth remains an open question. One prevailing hypothesis is the existence of methanogenic organisms on Mars. While similar microbes exist on Earth, they are extremely rare and cannot survive in most oxygen-rich environments. Understanding whether such life forms could thrive under Martian conditions remains a key focus of astrobiological research.